The physics of the microscopic world is quantum mechanics. So let's say I want to study the motion of an electron. What we do is we take the Schrodinger equation, we solve it, and we get what is known as the wave function solution. This wave function solution gives us an idea about the likelihood of where the electron might be. So it's a very probabilistic way of looking at the motion of an electron. Further, the theory can give us an idea about the average of a large number of measurements of, let's suppose, the position of the electron, which is known as expectation value. Now, all this is fine in the context of the quantum mechanical theory. However, if I suddenly zoom out of this microscopic world and come back to our reality, which is the low velocity macroscopic world, here we have a different theory. Here we have what is called classical physics, or more specifically, the Newton's laws. Here in this macroscopic world, if I want to measure the position or momentum of a particle, we can exactly do that by the Newton's second law. We can predict the exact position and the exact velocity of a particle as long as all forces and initial conditions are known in the context of the Newton's laws, and we can predict, let's suppose, the future trajectory of any kind of a particle simply by solving what is known as the Newton's second law. F is equal to dp upon dt. All right. So now the question is, if quantum mechanical theory is more general, if quantum mechanical theory is more true, then under what conditions the wave mechanical formulation of the Schrodinger equation leads to the Newton's second law? What is the bridge between this wave mechanical formulation of Schrodinger equation and the Newton's laws? Because at the end of the day, the Newton's laws are still valid, although in the context of the macroscopic low velocity world. That is what I am going to discuss today, because this bridge between the quantum mechanical theory and the classical theory is what is known as the Ehrenfest Theorem. The Ehrenfest Theorem gives us an idea about how we can find an analogy between the quantum mechanical theory and that of Newton's laws. So today I am going to derive the Ehrenfest Theorem based on our understanding of the expectation values of position and momentum. And more importantly, I'm going to give you an idea about those conditions under which the Ehrenfest Theorem gives us the Newton's second law. So let's begin. So we start with the expectation values of position and momentum. And if you're not familiar with what expectation values are, you might want to check my previous lecture in which I have defined these quantities and I've derived them from the basics of probability theory. So we start with first the expectation value of position, which is given by the expectation value of position is simply psi star x psi dx, where we make this integration for all of space because I am dealing with 1D systems where the particle is only restricted to the x-axis. In that situation, I integrate between minus infinity and plus infinity. And the expectation value of momentum is d by dt m times d by dt of x, which basically gives us, and I have given this proof in my previous lecture, minus iota h cut integration of psi star del psi upon del x dx, again between minus infinity and plus infinity. Now here I am going to take the time derivative of the expectation value of momentum. So if I take the time derivative of the expectation value of momentum, I'll just use this particular expression here. Again, if you're not sure how this came about, you can check out my previous lecture that contains the derivation for this particular expression. So this comes out to be minus iota h cut, which is a constant. I keep it out of the integration. And then I have del upon del t, where I have psi star del psi upon del x, and then I have dx here. I can use the chain rule to separate these terms, minus iota h cut. If I use this chain rule, I have del psi star upon del t, del psi upon del x, plus I have psi star and del by del t of del psi upon. I can actually interchange these derivatives because time and x are independent variables. So I can say del by del x of del psi upon del t, and because I'm integrating with respect to x here, dx. So now I want to substitute the Schrodinger equation to simplify these expressions. All right. So we know from the time dependent Schrodinger equation that minus h cut square upon 2m del 2 psi upon del x2 plus v psi is equal to iota h cut del psi upon del t. This is a time dependent Schrodinger equation. So if I rewrite this by taking this constant to the left hand side, then I can say that del psi upon del t. If I take iota h cut to this side, I am writing the right hand side in the left hand side now, okay? So this simply becomes h cut gets cancelled, 1 upon iota is minus. So this simply becomes h cut upon 2m del 2 psi upon del x2. And here I have v psi, but then I have minus iota upon h cut because this I have taken in the left hand side. Now if I take the complex conjugate of this particular expression, so let's suppose this is point number 1, the complex conjugate simply becomes del psi star upon del t. I am simply doing this because I want to substitute these terms here, okay? So this becomes h cut upon 2m del 2 psi star. Now here the wave function solution can be complex, so I am keeping it psi star here, del x2, and plus iota v upon h cut psi star. Keep in mind, this is point number 2, that v I am assuming to be real, okay? V is nothing but the potential energy function for that particular system. We usually deal with realistic potentials and realistic forces. So point number 1 and 2, del psi by del t and del psi star by del t, I'm going to substitute in these two scenarios, this expression and this expression here. Then what do I get? Let me write down. Small correction here. When I took the iota term from this side to the other side, it became 1 upon iota. So 1 upon iota is minus iota. So minus iota minus becomes plus iota in equation number 1, and the complex conjugate becomes minus iota here. So small modification in point number 1 and 2. All right. So now if I substitute them here in these two places, this simply gives us minus iota h cut integration of del psi star upon del t is point number 2. So here I have, let's say I put it in a bracket, minus iota h cut upon 2m del 2 psi star upon del x2 plus iota capital V upon h cut, you have psi star, okay, psi star, and then bracket close del psi upon del x. Here on the other hand, in the second term, I have plus psi star and del upon del x, and in the bracket we have del psi upon del t, which is iota h cut upon 2m del 2 psi upon del x2 minus iota capital V upon h cut psi, bracket close, and this entire expression is integrated with respect to x. So this is what we get, which is the time derivative of the expectation value of momentum after I have substituted the Schrodinger equation here. Now I want to simplify this, okay? So to simplify this, I'm going to go to the right hand side, but I'm going to rub this, okay? Just note this down. I'm going to erase these expressions here just to create some space. So let us look at this particular equation further, okay? So I'm going to simplify it by writing that here d by dt of the expectation value of momentum is simply equal to, I'm going to combine these two terms, the first and the third term into one integration, and the second and the fourth term into another integration, okay? So if I do that, so what happens? Iota h cut times iota h cut, what happens? So h cut square upon 2m, minus minus becomes plus, and iota square is minus. So here I get minus h cut square upon 2m integration. I have this particular term del 2 psi star upon del x2 times del psi upon del x, okay? This is one term, the first term. And what about the third term? In the third term, I will have a minus sign here, minus. I get psi star del upon del x del 2 psi upon del x2. Okay, this entire expression is integrated with respect to x. And then if I combine the second and the fourth term, I should get h cut gets cancelled. Iota becomes iota square, which is -1 times minus is plus. So I have here plus. So within the integration, I have v and psi star del psi by del x, psi star del psi upon del x minus psi star del upon del x of v psi, okay, because it is within the derivative v psi, okay. Again, this entire expression is being integrated with respect to x. So if I just take a look at this second integral, okay, let's just take a look at this particular integral that I have. All right, what is this? Here I have initially v psi star and then I have del psi upon del x, right, minus psi star del by del x of v psi, where psi is a function of x and v is also a function of x. So we can use the chain rule for the derivative. So this is going to give us psi star v del psi upon del x minus psi star psi del v upon del x, and the psi will come out. Again, integration with respect to x, okay. So here if you notice, these two terms gets cancelled, v psi star del psi upon del x minus psi star v del psi upon del x, because v psi star is same as psi star v, they are just functions of x, and all that is left is simply equal to integration of, or rather I have a minus sign, minus psi star del v upon del x psi dx. Now what is this? If you are familiar with how we define expectation values of different quantities in quantum mechanics, which we have discussed in the last lecture, how we find the expectation value of any quantity is that we take that particular quantity or the operator corresponding to that quantity and we sandwich between psi star psi and integrate for all of space, which is in this case minus infinity to plus infinity. So this essentially gives us the definition for the expectation value of the potential with respect to position. Now usually in realistic scenarios we deal with potentials which are most of the time position dependent or space dependent and not necessarily time dependent. So making that assumption, this then becomes an ordinary derivative. So I can simply say that this is dv upon dx expectation value, okay. So the expectation value of dv upon dx. Now what is minus dv upon dx? That is nothing but force, especially in classical physics. If we define conservative forces, then conservative forces are essentially the derivative of the potential with respect to space. All right. So now we have a expression that is now going to connect us to what forces are in classical physics. But I'm going to keep this here and then look at this first expression. So let's now take a look at this particular integration term. Okay. If I take a look at this particular integration term, then how can I simplify it? So if I take a look at this, this is essentially nothing but, so if I integrate, again I have a minus sign on this side, minus, I have psi star del upon del x and del 2 psi upon del x2, and then I have dx here. Of course I have a constant which I'm going to add later on. So what is this? If I use the integration by parts, then this simply becomes psi star integration, and you have del upon del x of del 2 psi upon del x2 dx minus becomes plus, and then you have integration of del psi star upon del x, and then here you have this particular term again. Let me write it in the second line, or maybe I should rewrite it. or let's keep the minus sign out of the picture. I'll introduce it later on. So this simply becomes integration of del upon del x, del 2 psi upon del x2, integration of dx, minus here you have del psi star upon del x, and then you have integration of del upon del x of del 2 psi upon del x2, integration of dx, and then this term is then multiplied to this term, and then we again integrate with respect to x here. Okay, so what is this? If you look at this particular expression, you have psi star and then del upon del x of some quantity integrated with respect to x simply gives us that particular quantity. So del 2 upon del x2. Now because this entire expression is being integrated between minus infinity to plus infinity, if I apply the limits here, minus infinity to plus infinity, we know that for any kind of a physical scenario, wherever we have a wave function solution, they always go to 0 and infinity. So wave functions are functions that has a large number of criteria associated with them, and for realistic scenarios, because we expect the wave function to be normalizable, we expect the wave function and its derivatives to go to 0 at infinity. So if I am evaluating a wave function or its conjugate and its derivatives at infinity, they always go to 0. This is an expectation we have in the this formulation of quantum mechanics. So now all that is left is minus. Here we have del psi star upon del x, and again I end up getting del 2 psi upon del x2, this integrated with respect to x. Okay, this is what we are left with. I hope that you are able to sort of compartmentalize these calculations. So this is the calculation for the third term, this is the calculation for the second term. And the second term essentially gives us this particular expression. So if I substitute this here back into this term and then look at these two expressions, okay, let's look at these first and the second term here. Okay, let me just, because the space is less and the calculations are always lengthy, I have to make sure that I organize them properly. Okay, so let's just quickly look at the first and the second term. Keep the constant aside, just look at the first and the second term. So the first term is what? First term is del 2 psi star upon del x2, and then you have del psi upon del x. Okay, this is the first term. And the second term I have evaluated to be, because this is 0, so we only have this particular expression. Essentially, this is the second term. Okay, so if I substitute, minus minus becomes plus, and then I am left with del psi star upon del x, and then I have del 2 psi upon del x2, and this is being integrated with respect to x. This can be simplified. Again, I'm keeping the constant out for the time being. This can be simplified by saying that this is a derivative with respect to x of del psi star upon del x, del psi del x. Okay, and then again the dx comes here. Okay, so if I do a derivative with respect to x of this term, del psi star upon del x times del psi upon del x, then I should get del 2 psi star upon del x2 del psi upon del x plus del psi star upon del x and del 2 psi upon del x2. It's kind of obvious from here. So again, del by del x of this function being integrated with respect to x gives us this. So if I just evaluate this, it should give us del psi star upon del x, and then you have del psi upon del x. Between the limits of minus infinity and plus infinity, what should this be? I just now told you we have these restrictions on the wave function solution that at infinity it should go to 0 as well as its derivatives. Alright, so therefore both these two terms at plus minus infinity goes to 0. So this entire expression comes out to be 0. So the first and the second term combined gives us what? It gives us nothing but 0. And the only thing that is left is the last term, which is this. So del by del t of the expectation value of momentum therefore is the negative of the expectation value of d by dx, which is the Ehrenfest theorem. So let me write this again here and we'll talk about it. Alright, so we have proved based on these earlier calculations that the time derivative of the expectation value of the momentum is equal to negative of the expectation value of the potential with respect to x. Now keep in mind that for a very simplistic scenario of conservative forces, we can represent the force as a gradient of the potential or a negative gradient of the potential. So I can write it as dv upon dx for an object moving in 1D. So what is this? This is nothing but the expectation value of the force experienced by the particle. So this is the Ehrenfest theorem, and we have derived the Ehrenfest theorem using nothing but the Schrodinger equation and the definitions of expectation values. So the quantum mechanical theory best gives us an idea of an equation of connecting the expectation value of position and something that is related to forces in this particular manner, which is closest to what we have in classical physics. However, I want to give a couple of more additional statements here. This is not exactly the Newton's second law, because if I'm interested in the Newton's second law in terms of the expectation value of momentum and the expectation value of position, then the Newton's second law would look something like this. Okay, because in Newton's second law, what we are doing is we are taking a force experienced by a particle at a given location, and then we are taking the time derivative of the momentum. And if I'm replacing these position and momentum quantities with their corresponding expectation values, then I should expect an equation that looks something like d by dt of the expectation value of momentum is equal to, let's suppose, the force experienced by the particle at the expectation value of position. So this is what I would expect if the Newton's second law would be correct, or I would expect, let's suppose if I write it in terms of the potential, this to look like something like dv at the expectation value of position upon d expectation value of x. So essentially, this is dv upon dx, I should say negative here. This is dv upon dx at the expectation value of x. So this would be the closest approximation to Newton's second law. So now, if I want to say that the Ehrenfest theorem does give us some information which is analogous to the Newton's second law, but there is a slight leap of faith here to go from this to this, I can kind of analyze what circumstances would lead to this kind of an approximation. So I can go from the Ehrenfest theorem to this particular version of the Newton's second law under two conditions. So let us try to understand those two conditions. To appreciate those two conditions, I am going to assume a potential which is slowly varying, okay? And then I am going to do a Taylor series expansion. So assuming a slowly varying potential, the reason I am taking a slowly varying potential is because I want to do a Taylor series expansion of the potential or its force, and then I only want to retain the first few terms and I want to exclude the higher order terms. So we can do the expansion either in terms of the potential or in terms of the force, it doesn't really matter. So let's do the expansion in terms of the force, for example. Okay, so what is this? This is minus, alright, so let's do the expansion in terms of this particular term. Okay, if I do an expansion of this particular term, can I come up with this particular term? So if I have a function of x, alright, so this is a force which is a function of x, I do a Taylor series expansion about x naught or expectation value of x. What is the expectation value of x? Expectation value of the x is essentially if I make a large number of measurements on a system or similar systems to find out the position of the particle. This simply gives us the average. So you can think of this as x naught, okay, the average of all those positions. So if I expand the potential, slowly varying potential or force or Fx, okay, then this simply gives us around the expectation value of x, f at x naught, or expectation value of x plus x minus expectation value of x times the first order derivative of fx at expectation value of x, and then you have plus half, and you have x minus del x square f double dash of the expectation value of at the expectation value of x. Okay, and then you have higher order terms, but let's suppose we take a slowly varying potential, so we can exclude the higher order terms. So in terms of potential, what we have is, in terms of potential, I will have a del cube v upon del x cube term here, and the other terms I am kind of ignoring. So in that kind of a situation, can we simplify this expression? So for that, here I have the expectation value of fx. So now, if I look at the expectation value of fx, what do I get? Okay, the expectation value of fx is nothing but if I take the expectation value of each of these individual terms. So here I have the expectation value of fx at expectation value of x. I should call it x naught, right? Every time I'm saying expectation value of x, I should just say x naught. So this is just x naught. Okay, that would sound better. Okay, so this particular term, and then I have here, so now keep in mind that what is this term? This term is nothing but the force experienced by the particle at x naught, as opposed to this term. This term is the average of all the forces experienced by the particle at various locations. So keep in mind, this term, which is the expectation value of the force, is the average of all the forces experienced by the particle at all locations. On the other hand, this term here, this term f of x naught, is the force experienced by the particle at x naught. All right, so the force experienced by the particle at x naught is just a number. It's just, let's suppose, a constant, because at a given location for one system, the particle cannot experience multiple forces. There can't be a large number of different forces that the particle experiences at the same location at that given instance. So therefore, the average of the force experienced by the particle at x naught is that number itself, right? Because we have just one value, there is no point writing expectation value of f of x at the expectation value of x. This is just this number, because this is just a number, right? If the particle experiences just one overall net force at a given location, then this is just the force experienced by the particle at x naught or at the expectation value position. So I need not write mean of this particular term, right? Similarly, now the next term here, I have the expectation value of x minus the expectation value of x overall, and again f dash x naught is again just a number, right? Because finally what we are doing is we are just evaluating the force at x naught, taking its first derivative, taking its second derivative. It's just a number, right? Or we can think of in terms of potential, second order derivative potential or third order derivative potential at x naught. So at x naught, it's not going to be some sort of a function, it's just going to be some value, because we are evaluating at a particular location. So I can take it out of this, and this simply becomes f dash, again x naught, and here I have half of x minus expectation value of x square and its mean, and this again is a number, I can take it out, f dash x naught. Okay, I'm calling x naught to be just the expectation value of x. This sounds simpler. So now what we can do is we can evaluate some of these terms. Okay, if I evaluate, let's suppose this term x minus x naught, its average. What is this? If I just use a definition of expectation value of position, I can evaluate this particular term to be simply integration of, what is the expectation value? You sandwich that term between psi star and psi. So I have psi star and you sandwich x minus x naught between psi star and psi, and then integrate between minus infinity plus infinity. What does this become? This is nothing but, if I separate the terms, psi star x psi dx minus, you have psi star again x naught psi dx. Okay, so this is just x naught, right? This is just one location for a given system. And because this is just one position, it's a constant, I can take it out of the integration. This is nothing but what? This is the expectation value of x. Here I take the expectation value of x out of the integration. This is nothing but psi star psi dx. For normalized wave functions, this is just nothing but expectation value of x minus expectation value of x. This comes out to be 0. So this term here is 0. All right. But what about this particular term? And if you look at x minus average of x square, now this is something which is called variance, or the square of the standard deviation. And it is not necessarily equal to 0. If you have studied statistics, if you have a distribution of data points, then the expectation value represents the average, while x minus the mean represents a set of data points. Their average may come out to be 0, but the average of their square is not necessarily equal to 0. So this I am going to call as sigma. Okay, so I am going to call this as sigma. Sigma is known as variance. It basically gives us an idea about the spread of the distribution. So in this situation, it will give us an idea about the spread of the wave packet or the wave function solution. So I think I should say this is sigma square. Okay, so sigma square is a variance and sigma here represents a standard deviation. So if I substitute these two things in this particular expression, so therefore the expectation value of force therefore ends up becoming the force at x naught minus 0 plus half of, again, this sigma, which basically is just another number that gives us an idea about the spread of the distribution or the spread of the wave packet. Square, again, because this is a number, its average will come out to be the number itself. So sigma square, and then I have the second order derivative of the force at x naught. Okay. So now what did I say? I said that the Ehrenfest theorem will replicate the Newton's second law for the expectation values of position and momentum under what condition? Under the condition in which this term vanishes. So if you look at the expectation value of force, this is equal to the force experienced by the particle at the expectation value of position plus some term, right? So now if this term vanishes, then I should get a very simple relationship from the Ehrenfest theorem to the Newton's second law. So what are those conditions? So the Ehrenfest theorem, which is the time derivative of the expectation value of momentum, is equal to the negative gradient of the potential expectation value, or we should say force experienced by the particle expectation value. This gives us the Newton's second law, which is, at least for the expectation value of position and momentum, which is time derivative of the expectation value of position is equal to the force experienced by the particle at the expectation value of x, which we can say is the best approximation of the Newton's second law in terms of x naught and p naught. All right. Now this happens when under two conditions. Okay, what is the first condition? If you look at f double derivative of x naught, this will go to 0 for a very unique potential, which is the potential of the harmonic oscillator. So if you look at the harmonic oscillator, what is the harmonic oscillator? The harmonic oscillator is a very unique potential in which the potential itself is directly proportional to some second order power of x. So then you have forces Fx, which is proportional to x. So if you look at that situation, the first derivative of f will be a constant and the second derivative of f will be 0. So for the case of a harmonic oscillator, the second derivative of the force, or we should say the third derivative of the potential at the expectation value will be equal to 0. Okay, so this term will come out to be 0. In that situation, the average of the forces is equal to the force at x0, which gives us the Newton's second law for the expectation values of position and momentum. So that is one scenario in which the Ehrenfest theorem gives us the Newton's second law for the averages of momentum and the averages of position. Okay, and then for general case scenarios, what about general cases where we are not stuck to a unique potential? So for a general case scenarios, we want this particular term, the sigma term, to go to 0. Okay. Now, how can that happen? That happens whenever we have a highly localized wave packet. You know, I said that sigma square, which is the variance, gives us an idea about the spread of the distribution. Here we are talking about the position distribution, which is essentially giving us an idea about how the wave function or the wave packet of the particle is spread out. If we have a highly localized wave packet, if we have a wave function which is confined to a very tiny region, so that if we are analyzing the motion of a particle, then the wave packet is confined to a very tiny region compared to the motion of the particle or compared to the slowly varying potential, then we can say that this is almost equal to 0, and therefore we end up getting the Newton's second law corresponding to the expectation values of position and momentum. So this is nothing but the bridge between the quantum mechanical picture and the classical mechanical picture, where instead of having force is equal to time derivative of momentum, we have the force at the expectation value of position is equal to the time derivative of the expectation value of momentum. So in the classical picture, we have nothing but, let's suppose, a trajectory of the evolution of a point mass particle, right? Where we have a position associated with the particle, where we have a momentum associated with the particle, and then we say in the Newton's second law, F is equal to dp upon dt. Okay. Now, what happens in the quantum mechanical picture? In the quantum mechanical picture, we have nothing but a wave packet or a wave function solution. If the wave function solution is extremely localized, highly confined in a tiny region, by that I mean the spread of the wave function in space, or the spatial extension of the wave function is extremely small compared to the region in which the particle is moving, or the region in which the potential is varying. In that situation, I can come up with a similar analogous equation of the particle's trajectory, let's suppose like this. Okay. In the classical world, when we measure position and momentum, we get unique specific values. But in the quantum world, we get a distribution of values. So we are looking at that limit in which the spatial distribution of the wave packet is so small that we are only looking at values which are close to x0. So x minus x0 should be nothing but 0. So this kind of a limit is only possible where we should say that the probability of the particle's position is equal to a delta function of x minus x0. If this is the case, then the expectation value of position and expectation value of momentum will be analogous to the Newton's second law. That means the expectation value of position and momentum will follow classical trajectories. So this is how we can bridge the ideas of quantum mechanics to that of classical physics. I hope you have understood what we have talked here, and it has given you some sort of a clarity to the subject of how we can connect the quantum mechanical picture to the classical picture. So that is all for today. We will talk further in our coming classes. I am Divya Jyotidas. This is For the Love of Physics. Thank you so much. Take care. Bye-bye.